Welcome everybody to the next video in our series on probability and statistics. I am Dr. Lathram, and today we will be talking about multivariate expected value, covariance, and correlation. So let's begin with usual definitions. So something that should be pretty familiar to us from our previous definitions of expected value is the multivariate case for expected value. So let's begin with a function g of y sub 1 and y sub 2, and y sub 1 and y sub 2 are two random variables. We'll assume that y1 and y2 has a probability density function, little p, of y sub 1, y sub 2. Then for the expected value of g of y sub 1, y sub 2, in the discrete case, it's calculated or denoted by e of g of y1, y2, and it's calculated as a sum over both y sub 1 and y sub 2, so all possible values of y sub 1 and y sub 2. And what you're summing is g of y sub 1 and y sub 2 times the probability of y sub 1 and y sub 2. So that's very, very similar to what we saw with our expected value in the single variable case. How does that generalize to the continuous case? Well, pretty much how you would expect. Instead of summing over all possible y sub 1 and y sub 2, we integrate over all possible y sub 1 and y sub 2 of g of y sub 1, y sub 2 times our probability density, p of y sub 1, y sub 2, dy1, dy2. Continuing with our definition, so we've kind of defined expected value. Now something that will be similar to variance for two random variables, y sub 1 and y sub 2, we'll define the covariance of y sub 1 and y sub 2. And it's denoted COV of y sub 1, y sub 2. And it's actually calculated as the expected value of the quantity y sub 1 minus mu 1 times y sub 2 minus mu sub 2. Now what are mu sub 1 and mu sub 2? They are the expected value of y sub 1 and the expected value of y sub 2 respectively. Now when we're calculating the expected value of y sub 1 and y sub 2, these values mu 1 and mu 2 are computed with respect to the marginal distributions. So the marginal distribution for y sub 1 and the marginal distribution for y sub 2 that were defined in the previous multivariate video. So if you need to go back, review that, take a look at those marginal definitions for marginal distributions. Now if we let y sub 1 and y sub 2 be random variables, then just as in the single variable case we had a simplified version of computing the variance, we have a simplified version of computing the covariance. So the covariance of y sub 1 and y sub 2 will actually be equal to the expected value of y sub 1 and y sub 2 minus the product of the expected values for y sub 1 and y sub 2. So let's see why that might be the case. Well, we start off with our definition. So the expected value of the product of y sub 1 minus mu sub 1 and y sub 2 minus mu sub 2, if we expand out everything that's in the parentheses, we'll get this expression. So y sub 1, y sub 2 minus mu sub 1, y sub 2 minus mu sub 2, y sub 1, and then the product mu sub 1, mu sub 2. Well, now we're going to apply the linearity properties of our expected value. So our expected value linearity means that this expected value will distribute across these sums and differences, and any constants can be pulled to the outside. So mu sub 1 and mu sub 2 are both constants. So if we apply that distributive property and then pull out the constants, then we have this expression. Well, now the expected value of y sub 2 and the expected value of y sub 1, those are just mu sub 1 and mu sub 2. And so what happens, we have this expression, so one of our values for mu sub 1 and mu sub 2 cancel out, and so we're left with the expected value of y sub 1, y sub 2 minus the product of the expected values. So now let's look at the relationship between covariance and independence. Well, if y sub 1 and y sub 2 happen to be independent variables, now independence was defined in the previous multivariate video, then the covariance for y sub 1 and y sub 2 will be 0. So let's see why that might be the case. So looking at the proof, if y sub 1 and y sub 2 are independent, then from the definition, the joint PDF is going to be a product of the marginal distributions. So looking at the continuous case, what that means is that if we look at the expected value of the product y sub 1, y sub 2, then that's going to be integrating from minus infinity to infinity, minus infinity to infinity for both y sub 1 and y sub 2 of this product. Now our PDF would go here, but the PDF is the product of the marginals. And so what happens, P1 of y sub 1 and y sub 1, this has no dependence on y sub 2 at all. Likewise, P sub y sub 2 and y sub 2 have no dependence on y sub 1, and so for this inner integral, we can pull the P sub y sub 2 and the y sub 2 to the outside as constants, and what that in essence gives us then is an integration over the products. Well, from the definition of our expected values, we compute the expected value with respect to the marginals. So we have the marginal of for y sub 1 and the marginal of y sub 2, and that's what we get of mu sub 1, mu sub 2. So then from our immediately previous theorem, how we calculate our covariance, the expected value of y sub 1, y sub 2 minus the product of the expected values gives us mu sub 1, mu sub 2 minus mu sub 1, mu sub 2, and sure enough, we get a value of 0. So that if we've got two independent random variables, we know for sure that the covariance between those two random variables will be 0. So that's only going to be part of the picture when we're looking at the connection between covariance and independence. Well, as it turns out, if two variables are independent, then we know the covariance is going to be 0. But that's a necessary condition, but not a sufficient condition. That just because we have the covariance being 0 doesn't necessarily mean that we guarantee independence. So let's take a look at an example to see that that's going to be true. So let's say that we've got a discrete random variables y sub 1 and y sub 2. We have y sub 1 written across the top taking values of -1, 0, and 1. Y sub 2 taking values of -1, 0, and 1. And we've got this very symmetric probability distribution that we have written in this table form. Well, if we calculate the marginal distributions, and now you begin to see, well, why are marginal distributions be called marginal distributions? Because when our data was written in table form, in order to get the marginal distribution, so if I wanted the marginal distribution for y sub 2 at -1, I'm summing across all possible values of y sub 1, so that means I'm summing across this row. So where was the most natural place to put that particular probability distribution? In the vertical column at the end of the table. So in the margin, the vertical margin for the table. Just like if we wanted the marginal distribution for y sub 2, now we're summing across all possible values, or y sub 1, we're summing across all possible values of y sub 2, so we're summing down all of the columns. And so that ends up being in the bottom margin of our table, hence the name marginal distributions. So if we calculate that, we can see that if we sum across the rows, we're going to get 3/16, 1/16, 1/16, so 5/16, 6/16, and 5/16, and we see that those things are going to be the same for y sub 1 and y sub 2. Now, to see why we fail to have independence, if we pick one particular value, so let's look at P of -1, -1. So our joint PDF of -1, -1 is 1/16. So if you don't, just taking a look back, here's our distribution. So for -1, -1, it was 1/16. But if we look at the product of the marginals for -1, -1, we see that we in fact have 5/16 times 5/16 And so we end up with 25 over 256. Now that's not going to be equal to 1/16. And so our joint PDF is not a product of our marginals. And so for that reason, y1 and y sub 2 are not independent. Well, let's calculate the covariance of those things. So if we look at the expected value of the product of y sub 1 y sub 2, so we're looking at all possible values. So if we make that calculation, we see sure enough that we get an expected value of 0. And if we look at the expected values of for each individual variable, so the expected value of y sub 1 and the expected value of y sub 2. Now remember, these are computed with respect to the marginals, the marginal distributions that we have, and sure enough, they end up with an expected value of 0 as well. Our distribution was very symmetric. And so what happens when we compute the covariance? We end up with 0 minus 0. So we've got a covariance of 0. And so what that means is exactly what we said before, that covariance being 0 is a necessary condition, but it is not sufficient. So if they're independent, my covariance of 0. If I have a covariance of 0, I may or may not have independence in that case. So my condition only goes one direction. So now things that naturally go along with the topic of covariance are something that we see quite often in statistics. You'll see people talk about correlation coefficients. So let's see what those things are. Well, if we have y sub 1 and y sub 2 are random variables, then the correlation coefficient is defined to be the covariance of y sub 1 and y sub 2 divided by the product of the standard deviations for y sub 1 and y sub 2. Now sigma 1 and sigma 2 are the standard deviations, so remember those are the square roots of the variances, and those things are computed with respect to the marginal distributions for y sub 1 and y sub 2 respectively. So now correlation coefficients have a really nice property to them, and this is why everybody talks about them in this particular setting, and that they are guaranteed to take on values between -1 and 1. And so let's see why that would necessarily be true. So we start off with the expected value of y sub 1 minus mu sub 1 over sigma sub 1 quantity squared, and y sub 2 minus mu sub 2 over sigma 2 quantity squared, that those will have expected values of 1. Now, you can say, why might that be true? So we know that. How do we know that? Well, use your linearity properties. So use your linearity properties, multiply these out, convince yourself. So as a little bit of an exercise, if you multiply one of these out, use your linearity properties and the definitions of mu sub 2 and sigma sub 2, and see if you can't convince yourself that that will be true. So our next step is to see that, if we take the difference of those two things and square it, if we look at the expected value of that, it will be non-negative. So, it will be non-negative, so it'll be greater than or equal to 0. Well, why would that be the case? Again, this is another one of those places that you can convince yourself, why is that going to be true? So just to give you a little bit of a hint, go back to your definition of expected value. So you're integrating or you're summing a product of things. So I'm integrating, I know my probabilities are always positive. If it's squared, I know something about the sign of those values, and so you can convince yourself that this would necessarily be a true statement. Alright, so now let's take that expression and let's expand all of this. So if we do, so we're kind of taking this as a bit of a FOIL property. So what do we have? The square of the first one minus 2 times the product of those two values plus the square of the second one, and then we've also used the linearity properties of expected value. So if we've distributed the expected value across the terms in that expansion. And then we've taken out these constants, 2 over sigma sub 1 and sigma sub 2. Now, what this means is that from our previous example, now these values were 1. This value was 1. And since this was positive, we have 0 is going to be less than or equal to 1 minus 2 over sigma sum 1 sigma 2, and the expected value of this expression plus 1. Well, if we kind of rearrange things, so we put our 1's together, we move the 2 over to the other side, and sure enough, we see that the expected value of y sub 1 minus y mu sub 1 times y sub 2 minus mu sub 2 over sigma sub 1 and sigma sub 2, that's going to be less than or equal to 1. And so that is our correlation coefficient. Well, now we can do a similar calculation, but now we're going to take the sum. So again, we're taking the expected value of something that's positive, so that's going to be greater than or equal to 0. And if we kind of do the same kind of expansion, our values, rearranging terms, so there's a little bit of algebra between this step and this step, but using the first one as a guide, I think you'll be able to convince yourself, work through the details of that, and verify for yourself that this statement is going to be true. And so what happens as a result, we have our correlation coefficient sandwiched always in between -1 and 1 inclusive. So now let's look at a couple of theorems that involve situations where we have multiple random variables. So if we've got y sub 1, y sub 2 up to y sub n be random variables, so they don't necessarily have to be independent, so they're just random variables, and we happen to know that the expected value of y sub I is mu sub I, then if we take some real numbers, a sub 1 all the way up to a sub n, and we're going to define a new random variable that will be the linear combination of a sub I and y sub I using the a sub i's as constant. So if u is going to be the sum from 1 up to n of a sub I, y sub I, then I've got a probability distribution associated with u, and I know that the expected value of u will then be the linear combination of the expected values for the y sub I. So it will be the sum from 1 up to n of a sub I times mu sub I. But then I also know that the variance of u will be the sum from 1 up to n of a sub I squared times the variance of each y sub I, plus this kind of correction that I have here for 2 times the sum over all possible I and j, so I can do that as writing 2 times I strictly less than j, so where they're not equal, of the product of a sub I, a sub j times the covariance of y sub I and y sub j. Now to see why that might actually be true, I'll kind of leave that as an exercise, but just to give you a little bit of a hint, if you want to try that on your own, which you really should try that on your own, it's really nothing more than looking at the linearity properties, so applying those linearity properties of expected value again. Takes a little bit of manipulation down here for the variance, but again, just multiply everything out, be very careful with your indexing, and apply the linearity conditions for expected value. So another theorem that will come up quite often, and we'll use it later on, will be if we have two sets of random variables, so y sub 1 up to y sub n and x sub 1 up to x sub m are random variables. We have the expected value of the y's being mu sub I, the expected value of x sub j being mu hat sub j. Then we're going to take combinations, linear combinations of the y sub I, and call that u sub 1. Linear combinations of the x sub j's using the b sub j's, call that u sub 2. And if we look at the covariance of these two new random variables, u sub 1 and u sub 2, again that's going to be a product, or a sum over all possible i's and j's, of a sub I times b sub j times the covariance of y sub I and x sub j. So again, how do you come up with that? It's really nothing more than writing our definitions of covariance in terms of the sums, expanding the differences, and applying linearity properties. So again, that's a good exercise. I encourage you to take the steps through that and kind of verify that theorem for yourself. And so to kind of finish up this video, we'll talk about change of variables for the multivariate case. So if we have y sub 1 and y sub 2 are continuous random variables, they have joint PDF of little f, then on this set y sub 1, y sub 2, where our PDF is positive, we apply a one-to-one transformation into new variables. So we've got new variables u sub 1, and u sub 1 is a function of y sub 1 and y sub 2. And u sub 2 is some other function that we're going to apply of y sub 1 and y sub 2. And these functions of y sub 1 and y sub 2 are invertible. So there is the inverse transformation. So I've got a one-to-one transformation, so I've got an inverse transformation. So that I am able to actually write y sub 1 in turn as functions of u sub 1 and u sub 2. And I can write y sub 2 as functions of u sub 1 and u sub 2. Now, for this inverse transformation, I'm also going to assume that y sub 1 and y sub 2 as functions of u sub 1 and u sub 2 have continuous partial derivatives. And so if I look at the Jacobian of the transformation, so if you're not familiar with that, or it's been a while, go back and take a look at your Calc 3 textbook. And when you get to multivariate integration and multivariate change of variables, your Jacobian is going to pop up there, and that should give you something that's kind of familiar. So go back and look at that as a reference if it's a little bit rusty. And so the Jacobian is calculated as the partial of y sub 1 with respect to mu sub 1, y sub 2 with respect to mu sub 2, y sub 2 with respect to mu sub 1, and y sub 2 with respect to u sub 2. And so for the Jacobian, I'm calculating the determinant of this, so it's the product of these two minus the product of those two. Again, go back, take a look at your Calc 3 textbook. Then what's the conclusion of that? The conclusion is that the joint density function of these new variables u sub 1 and u sub 2, which I could write as g of u sub 1 and u sub 2, that's calculated in a similar way for our single variable case. So we've got our joint PDF for y1 and y2. We're substituting in our inverse transformations, and in the single variable case, we had the absolute value of the derivative. Well, now in the multivariate case, we've got the product with the absolute value of the Jacobian of the transformation. And so this gives us a way to change random variables in the multivariate case. So I hope that you've enjoyed this video, apply some of the stuff that's in it, and I will see y'all next time.